Well, in this video, we're going to learn about matrix row operations that are legal, so to speak. Let me show you what the goal is first. In the previous video, we showed a couple of examples of, of matrices. This one would take us longer to solve than this one would. This one's considered to be in row echelon form because we have ones down the diagonal and zeros underneath that diagonal. So, our goal is going to be a matrix that might look like this and use some row operations that are going to change the values of the matrix and get it into one that looks more like this form, where we have ones down the diagonal and zeros below those ones. So that's our goal. And here are the three matrix row operations that you're allowed to do on a matrix. And what do I mean by allowed to do? Well, let's just read on. The matrix row operations, performing any of the following three row operations will not change the solution set for the system of equations. So, we'll use these three row operations on an augmented matrix in a certain way so that the resulting matrix is in row echelon form, which means, again, the ones go down the diagonal, zeros underneath, and then these could be any numbers we want. When I put an asterisk, that's kind of sometimes thought of as a don't care condition. It can be any number you want. All right, so we want to get it into this form. Well, here's what you're allowed to do. You can interchange any two rows. Simple as that. And when we're writing a new matrix, we want to indicate what we are doing. So this is kind of the terminology we'll use, the symbols. This means switch row I with row J. So one example, row 1 is switched with row 3. So where row 1 is, you put it in the row 3 slot, take row 3 out, and you put it in the row 1 slot, meaning interchange those two rows. Another thing you're allowed to do is multiply any row by any non-zero number. I didn't even have to put the divide, because if you need to divide it by 2, well, that's the same as multiplying it by 1/2. So I didn't even have to write this divide. But you can multiply or divide any row by any number other than 0. And basically you would write this. K is just some number times row I. That means take row I, multiply it by this number K. And that means multiply every term in the row by this number K. So for example, if I say -3 row 2, it means -3 times row 2. So I'm going to multiply row 2 by -3. And once again, it means every element in the row gets multiplied by -3. Okay? And then, this is the one we're going to use probably the most. To any row, you are allowed to add, and you don't need subtract. I'm going to go ahead and say add. You can add any multiple of any different row. And why don't I need that subtract? Because the multiple could be a negative multiple. In other words, this K can be a positive number or a negative number. So I didn't really need to say or subtract. So to any row, you can add any multiple of another row. So what these symbols mean is row I, what you need to do to row I is add K times row J into it. So row I is the row that's going to change. And you're going to add row J multiplied by the number K into this. It's a perfectly legal row operation. So here's the example. Row 2 plus 3 row 1. So all that means is you're going to go to row 2, and you're going to, somewhere on the scratch paper, you're not going to change row 1, but somewhere you could write out what 3 times row 1 is, and then just add it into this row. So add 3 times row 1 into row 2. So those are the three row operations that will not change the solution. So if we can use these in a nice way to get our matrix into this form, it just makes it easier to solve. And by the way, this is very similar to how a computer would solve this system of equations. it would take the original one and it would convert it into a matrix more like this. And then again, once we know this, we can easily get the bottom row. And then we'll end up doing back substitution, but I'm getting ahead of myself. Okay, number 5. Just a definition. Two matrices are row equivalent if one of those matrices can be obtained from the other by a sequence of row operations. And as long as they're row equivalent, they have exactly the same solution. So we'll take one that's ugly and we'll do some row operations until it's one that's nicer to work with. But they'll be row equivalent, and the second one will be easier to solve than the first one. Okay, so here we're going to do this. I chose to do this example. We're going to use a method called Gaussian Elimination to solve this system of equations. And I'm just going to do it here. Hopefully you can follow along with what I'm doing, even though I haven't exactly told you the recipe. In the next video, I'm going to tell you the recipe. So it'll be easier to understand the recipe after you've just seen one example done. All right, here we go. Let's first write this system of equations as an augmented matrix. Excuse me. So the first row, 1, 1, 1, 3. 1, 1, 1, 3. Second row, 2, 3, 7, 0. Third row, 1, 3, negative 2, 17. 3, negative 2, 17. And then the vertical bar, again, just represents where the equal sign would go. Okay, the first thing I want to get is a 1 inside that box. Excuse me. Well, notice, for this example, it's done for me. My very basic first step is done. Now what I'm going to do is use this 1 to turn this into a 0, that 2, and 1 into a 0. I want to use that 1 to get zeros below it. So the way I'm going to do that is row 2. So remember, I'm not allowed to multiply a row by 0, so I can't do that. And switching rows won't do it, so the only other option I have is to add a multiple of a row into row 2. And what I'm going to do is I'm going to take row number 1 without changing it, minus 2 times row 1. I put a minus sign there. I could have said row 2 plus negative 2 times row 1. But it's the same thing as row 2 minus 2 times row 1. And I could even make a little note up here. 2 row 1 is equal to 2, 2, 2, 6. It's that 2 right there that I need because I'm going to do a subtraction. Or I could actually do negative 2 row 1 is negative 2, negative 2, negative 2, negative 6. So if I want to perform the row operation, row 2 minus 2 times row 1, all I have to do is take row 2 and add negative 2 times row 1 into it. So now that negative 2 and 2 will give me a 0. All right? Well, I'm going to do it all in one step. In my next matrix, I also want to turn this into a 0, which would be row 3 what? Again, we always want to use the one that we just created, or the one I put the box around. All I have to do is do row 3 minus row 1. That's it. And that, normally then I put an arrow like that. And this will be my new matrix. Notice row 2 and row 3 are changing. Row 1 does not change. 1, 1, 1, 3. I'm having to go down a little bit of an angle to avoid this. Sorry about that. Okay, so row 2 minus 2 row 1. it's going to be the same as row 2 plus negative 2 times row 1, which is right here. So we'll get a 0, and then a 3 and a negative 2 is a 1, 7 and negative 2 is a 5, 0 and negative 6 is a negative 6. All right, so if you didn't want to write this out, let's just pick one of these. The number 7, we're in row 2, minus 2 row 1 would be 7 minus 2 of this. 7 minus 2 times 1. That's where the 5 came from. This is 3 minus 2 times 1. That's where the 1 came from. 2 minus 2 times 1. That's where the 0 came from, and I think I skipped this one. 0 minus 2 times 3 is negative 6. Okay, the third row. All we have to do is take this row, term by term, subtract row 1 from it. So it's going to go 1 minus 1, 0. 3 minus 1, 2. Negative 2 minus 1 is negative 3. 17 minus 3 is 14. Okay, that is kind of the main step 1. You get a 1 in the top left corner, and then you get zeros below it. And now what we do is we've got this much done, and 0. Then we go to this. We turn this one into a 1 and get zeros below it. And then we go down here to this one, turn that into a 1 and get zeros below it, although there's no other rows underneath it, so that would be the end. Okay, so we got this for free. We didn't have to do any work to get that 1 there. If this number happened to be 1/2, then a nice way to fix that would be multiply the row by 2, because you need to convert this into a 1. But we got that for free. All right, so now that we have this 1 in the second row, the second pivot here, we need to get a 0 below it. So let's see if I have enough room to go to the right. What would be the row operation to turn this 2 into a 0? And we want to use the 1 that we just created above it. It would be row 3 minus what? Minus how many row 2's? Well, if I just subtract row 2, it's going to be 2 minus 1. That's not going to get me a 0. I need row 3 minus 2 row 2's. Hope I said that correct earlier. We're using this 1, which is row 2 in row 2. So we're taking row 3 minus 2 row 2's, and that's going to give me a 0 here, and that's the goal. Okay, the first row does not change. And the second row doesn't change. 0, 1, 5, negative 6. The third row changes. So if you wanted to, you could write down what negative 2 times row 2 is somewhere under the side. Negative 2 times row 2 would be 0, negative 2, negative 10, positive 12, because negative 6 times negative 2 is positive 12. So row 3 minus 2 row 2's is going to give me a 0 minus 2 times 0, which is 0. A 2 minus 2 times 1 gives us 0. That was our whole goal. What is negative 3 minus 2 times 5? Minus 2 times 5 would be minus 10. So negative 3 minus 10, negative 13. Okay, what's this going to be? It's going to be row 3 minus 2 row 2. So it's 14 minus 2 times 6. Minus 2, sorry, negative 6. Minus 2 times negative 6 is the same as plus 12. Negative 6 times negative 2 is 12. 14 plus 12, 26. Oh, I was hoping for a good number there, because this negative 13 was worrying me. But we have negative 13 and 26. So we have one more matrix to do and we're done. So I'm going to maybe make it right here, right below this one. So we create, let's go back to the beginning for a sec. We got this one, we got zeros below it right here. Then we got this to be a 1, and we got zeros below it. So what's the next thing we do? We're going down the diagonal. This negative 13 needs to become a 1. So how do you do that? There's only one way to do it. You just divide by negative 13, which I could write as negative 1 over 13 times row 3. If you wanted to write, row 3 divided by negative 13, that's perfectly fine as well. That's not 73, that's negative 13. We're dividing it by negative 13, which is the same as multiplying it by negative 1 over 13. So row 1 and row 2 stay the same. It's the third row that changes. All we're doing is dividing by negative 13, so it gives me a 0, 0, 1, and then 26 divided by negative 13 would be a negative 2. We just completed Gaussian elimination. We started with a matrix that had no zeros in it, I mean that one, but had only that as a 0. And we used legal row operations to turn it into one that is in row echelon form. 1s down the diagonal, 0s below it. Now, if you try to do it out of the order that we just talked about it, you might run into problems. Because once you get a 0, you don't want to corrupt that 0. So if you follow the instructions, it works every single time. So we were asked also to solve this. So let's just solve it. What does the bottom row tell us? 0x plus 0y plus 1z is negative 2. So remember, this is the x column, the y column, and the z column. So I know that z equals negative 2. That's what I got from row number 3. Now we're doing what's called back substitution. If z is a negative 2, what's the equation associated with row number 2? It's 1y, which is y, plus 5z plus 5 times negative 2, because we already computed z is negative 2, equals negative 6. So y plus negative 10, so I'm going to make that minus 10, equals negative 6. Add 10 to both sides, and we get y equals, adding 10, would be a positive 4. Okay, so now I know what z is. I know what y is. I need to go back up to row number 1 to figure out what x is. The row number 1 is x plus y plus z is equal to negative 3. I'm sorry, positive 3. So that would be the same as saying x plus 4, because that's y, plus negative 2, because that's z, equals 3. So x plus 2 equals 3. I just combined the 4 and the negative 2 to give me 2. Subtracting 2 is going to give me an x equal 1. Okay, so that is the solution. We've got x, y, and z. Now, instead of when we had two equations with two variables, we always used an ordered pair x, y for the solution. In this case, we make it an ordered triple. So the solution can be written as 1, make sure you do it x, y, z in the correct order, 1, 4, negative 2. Again, I know we didn't discuss the recipe first. I discussed it, but we didn't have it written down formally. But we will see the formal recipe on how to do Gaussian elimination to solve a system of linear equations in the next video.